Okay, we're looking at Chapter 4, Lesson 1, and we're going to look at these Set 2 problems. It's really not a whole lot to these. We're applying a lot of the things we've already learned, but we're just dealing now with decimals and fractions because we're dealing with rational numbers. And again, we've already stated that a rational number is any number that can be written as the quotient of two integers. So there some complexity now to our problems, and they're not simply these integers that we were dealing with in the past. So let's go ahead and just take a look. We'll probably not do many of these, but we'll just indicate what they're looking for. In problem number 4, we're on page 152, set 2. Change each of the following rational numbers to decimal form by carrying out the indicated divisions. So again, we're not going to do all these. In fact, I don't think we really need to do more than one. Just to show you an example, I'm going to go grab my pen here. Make sure I have the right size and the right color. So let's put that first one up on the board, and we have 7 over 5. So we know we can write that as 5 being divided into 7. Now immediately you will see that our number is going to be more than 1 because there's definitely more than one 5 inside of 7. There's going to be something left over. So 5 into 7 goes how many times? Well, it goes once. We'll divide 7 by 5. We'll subtract 5 from 7 and we'll end up with 2. Now we'll need to create our decimal point and we'll add zeros. Now why can we add a 0? Well, because 7 is the same as 7.0. So we'll now divide 5 into 20, and we know that goes 4 times, and 4 times 5 is 20. So we have no remainder, which means that we have our answer. And our answer is 1.4. Okay, so now these are exercises of division that you've done, I'm sure, many times before, and they're fairly simple. I would expect you to be able to divide. In terms of using a calculator, we've been able to have discussions about using calculators, and I know that calculators make our lives a lot easier. I think these numbers are easy enough for you to be able to just do them by hand. Okay, but most importantly is that you understand the concept of the rational number. That number is 1.4, and that it can be expressed as a quotient, as we see 7 over 5, and we actually did that by dividing 5 into 7. So let's move on to number 5. Number 5, the number 0.3 is rational because it can be written as the quotient of two integers. Excuse me. We have 0.3. Make that a point, and that's equal to 3 over 10, right? So now one thing that's great about decimals is that you can express them in tens, hundreds, thousands, so they're very easily converted. We're going to have some of these down below. Show that each of the following numbers is rational by writing it as the quotient of two integers. Each part has many correct answers. So if we look at 4, the first one was 4. And what is 4 as we would write it as a quotient of integers? Well, we know we can divide 4 by 1. All right, 4 by 1. We can also divide 40 by 10, could we not? We could divide 400 by 100. So these are all, and as I said, many answers. There's an infinite number of answers actually to these, and certainly within the grasp of our knowledge and our ability to compute numbers, there's quite a few. Okay. When I say infinite, we can just keep adding and adding. In fact, you notice what's happening here is I'm adding 0 to 0 above and below. So I can go ahead and just keep adding a 0, right? And now 4,000 divided by 1,000, 40,000 divided by 10,000. How many 10,000s are there in 40,000? Well, there's 4 of them. So again, and these are both integers. So as I said, there are infinite number, and our mind can comprehend Probably up to a certain point, but we can always challenge it to look at the next number. We can simply add, but you could probably find a few answers just right off the top of your head for most of these. Now zero. Now zero. How can we show zero as being the quotient of two integers? Oh, well, we can say 0 over 1, could we not? That's certainly 0. Now, do we add 0 zeros? No, we can say 0 over 2, right? How about 0 over 3? And we can go on and on as the numbers go. I can say 0 over negative 1, and I can say 0 over negative 2, and I can put as many integers here. And again, here now we can really start looking at the infinite number of possibilities simply because we're dealing with so many numbers that are close to us, such as 1, 2, and 3, and negative 1, negative 2, and of course we could write here negative 3. So these numbers, we can get a lot of examples and not go near this. In fact, I can go 10,000 up and 10,000 down in terms of negatives, and that will give me 20,000 answers, and I'm just touching the surface of numbers that we deal with, right? So let's take a look at our next one, 0.7. So how would we show 0.7? Well, we know 0.7 is what? 7/10. That's the language that we would use. Notice we used it up here. 0.3 is 3/10, and we actually wrote it as 3 over 10. So we could simply do the same here. 7 over 10 is 0.7. And as I showed you above here, we can certainly say 7 over 100, right? Because 7 over 100 is also 7/10. Now you might say, but that's 70 100ths, Mr. Cartagena. Well, it certainly is as we're writing, but when you divide 70 by 100, you'll get 0.7. And I'm sure you've had some of the exercises in elementary math where you would just say, well, I've got 2 zeros here. I can just go ahead and eliminate these zeros. 1 0, that's at least on each, right? So if I had 500 divided by 6, my pen went a little crazy there. If I had 500 divided by 600 and I wanted to simplify that, well, I said, well, I can get rid of 1 0 here, 1 0 there, then 1 0 here, then 1 0 there. And that gives me 5 6. And is that equivalent? Well, sure, because it's the same as saying 5 times 100 over 6 times 100, right? And the 100s just simply eliminate each other because we can do that because they're factors. They're being multiplied. So we can look at this in many, many different ways. But at the end, what we're looking at here is we're able to express these as the quotient of two integers. Let's go ahead and take a look at a couple of others here. I'm going to clean up my board so we can have a little more room. And that's not cleaning it up. I'm just totally removing my board there. Okay. Now that's the wonders of modern technology. If it were only this easy for teachers when they're in classrooms. Let's go ahead and take a look at our next problem. We had 0.01. So now what we call 0.01 when we're speaking is 1/100th. Okay, if we were to say 0.1, we would say 1/10, but we know we moved over one decimal place, so we're now into hundredths. So just by saying this, we know that we can write this as 1 over 100, 1/100th. Okay, 6.5. Okay, that one's a little bit harder, isn't it? Well, 6.5. We know that that's 6.5, right? We can write that as a fraction. And if we can write something as a fraction, this is just, we know that we can convert that. 6.5, we know that, well, I can multiply 6 times 2 and get 12 and add 1, and I can call this 13 halves, right? I'm sure you've done that in math before. What is this really over here? Well, if we're going to represent the number 6 as a fraction, we can write it as 12 halves, right? 12 divided by 2 is equal to 6, and we simply need to add 1 half. And again, this is fairly elementary fractional work. Fractions are sometimes not a lot of fun for some of us because it does challenge us to think a little further. It puts limitations, but we do have a common denominator here, so our limitations are limited, let's just say, and we can actually go right ahead and add these two together and get 13 halves. So we need to think of things fractionally, and we need to go back into our memory bank and say, how did I do that years before? We have negative 2.9. Okay, negative 2.9. Okay, so they threw a negative in there just to introduce the positive and negative aspects of rational numbers. So we'll always carry that negative, but how can I write this as a fraction? Well, I can write this as 2. That 0.9, as we did before, we know we can write that as 9/10, right? So we could do something like this. Could we not? 2 and 9/10. And we can continue moving over and saying, well, 2 in the form of tenths. I want to be able to add the 2 and the 9/10, but I need to express the 2 in the form of tenths. Over here, we did it with halves. We expressed the 6 in the form of halves as 12 halves. So how many tenths do I need to make a number 2? And that's quite simple. It's 20, right? 20 divided by 10 is going to give me 2. And I still have the 9 over here. Now you might say, Mr. Cartagena, where's that negative? Well, we're going to put this all in here. We're going to write this properly. I would put my parentheses around here, and I'll put my big fat negative over here, okay? This is all going to be negative. So when I add these two, in the end, I'm going to give it that negative. In fact, I probably could have done that a little more down here so you could see where we're carrying the negatives, and that's what we'll do over here. Just put the big fat negative there. And what happens when we add 20 plus 9? Well, we get 29 divided by 10, right? We add these two, and we have negative 29 tenths. Okay, so that's our fraction. We're showing the two integers. Let's look at 3 and 1/7. Well, they're giving us one. That's pretty easy already because we already have it in fractional form. We just need to eliminate the mixed fraction, which is 3 and 1/7. Thinking again, how do I convert this to sevenths? Well, 3 would be 21/7. Now, just taking a step back to how we were doing it up here before, you can always multiply over here the denominator by the whole number. And that's going to give you your 21/7, right? 21. In fact, you may not even have to write what I'm doing if you're able to remember. Just 7 times 21, 7 times 3 is 21, plus 1, well, that's 22/7. All right, and if we would have done it the long way by simply writing out 21/7 plus 1/7. But we could do that in our mind. Quick shortcut there. 7 times 3 is 21, plus 1 is 22/7. Okay, and this helps to see it this way because it makes more sense by seeing it as the sum of these two fractions. And that's what you have here. You have 3 and 1/7. You don't have 3 times 1/7. We will be dealing with fractions like that when we say 3 times 1/7. That would be different than 3 and 1/7. Okay, and the word "and" obviously means addition. Let's go on to negative 8 halves. Again, they give us that negative to start with. And if I were to take my easy way, saying 2 times 8, well, we know the answer is negative. 2 times 8 is 16, plus 1 is 17 halves. Okay, so that's the quick way, and it's negative 17 halves. So that would be number 5.